Hello everyone. So today we have a Calc 2 question. Given the recursive sequence a sub n plus 1 equals the square root of 8 times a sub n plus 9 with a sub 1 equals 10, show that the sequence converges or diverges, and if it converges, find the limit as well. So when you're working with recursive sequences, it's hard to see whether it converges or diverges by just looking at it. So what we often like to do is to compute a few terms and see what's going on. So our first term, that's given to us, it's 10. If we wanted the second term, it would be square root of 8 times a1 plus 9. So again, remember that when you're working with a recursive sequence, the value of a term basically is dependent on a previous term or previous terms. So in this case, a sub 2 would equal 8 times a1 plus 9, the square root of that, which would equal the square root of 8 times 10 plus 9, or the square root of 89, and etc. If I wanted a sub 3, that would be the square root of 8 times a sub 2 plus 9, which would equal the square root of 8 times the square root of 89 plus 9. That's kind of, hard to figure out in terms of, whether these values are getting closer to something. So I would suggest we put these into a calculator, and if we do that, this would pop out for us. The square root of 89 is 9.43. The square root of 8 times the square root of 89 plus 9, the square root of all that is 9.19, and yeah, etc. So these are all the terms here afterwards, and as you can see, if it makes sense, at least to me, that your values are getting closer to 9. And also your values are decreasing, meaning that going from one term to the next, the terms are smaller than the previous ones. So yeah, so if I had 9.43 for the second term, 9.19 is the second, so it's smaller than the previous term. So graphically speaking, this is what's going on with having these dots here. So your terms are basically decreasing and they're getting closer to 9. So this is telling me this is going to converge. Now, how do I actually prove this convergence? Well, we're going to use this graph as a motivator, let's put it that way, to look at this theorem. So we have a theorem called the monotone convergence theorem, which says if your sequence is decreasing and bounded below, then it converges. If your sequence is increasing and bounded above, then it converges. Now the word bounded below basically means that all the terms are greater than some number, and the term bounded above means that all your terms are below a number. So for example, this would be an example of something that is decreasing and bounded below. So all the terms are greater than some number n, and these are also decreasing. And on the other hand, over here, your terms are increasing with this graph below, and they're all smaller than a value of m. And the idea with this theorem is, if you keep on going here, let's look at this picture. Say you're increasing and bounded above, then your terms kind of have to bunch up and get closer and closer, and they have to converge. And likewise, same thing is on here. If your terms are decreasing and they're always bigger than some number n, they have to converge. They have to get all closer to some value. Now the value itself is not necessarily m here, that line that I drew. It could be a value that it might be larger than m or smaller than m. It all depends. All right, so how do I go about proving both those conditions? Again, my sequence looks like that. Again, going back to the picture here, it's decreasing and it's bounded below. So I want to prove those two things, that it's bounded below and it's decreasing, and therefore I would show that it would converge. Now, this is a two-part video, and I'm gonna prove the bounded below part first, and I'm gonna use that to prove the decreasing part. And it's not like a lot of work, but I think it's best that I just split it up into two parts, basically because there's a lot of explaining though of why I'm doing such thing. And one piece of advice that I would have here is I would pause this video and try to work it out yourself, and just see what you come up with. Okay. Now, we want to use some technique here, and I'm going to use what we call mathematical induction. If you're not familiar with mathematical induction, I would take a look. I'll link a video of it. And using mathematical induction, first of all, we have the base case here. So the base case is basically when we plug like the first value for which we say our formula is valid for. In this case, is A1. A1 is 10, which is greater than 9. And then we have our inductive step. And yeah, again, just as a reminder, we're trying to prove that it's bounded below, so the terms in your sequence are greater than 9. And the inductive step here is that you're going to suppose that a sub k is greater than 9 for a positive integer k. And you want to prove that ak plus 1 is greater than 9. So that's what we're trying to prove. So ak plus 1 here, this is what? Well, that would be the square root of 8 times ak plus 9. Now, we know that a sub k is greater than 9 by our hypothesis. And here's what I'm going to do. I'm going to build up like the square root you see here, what's inside the square root. So 8 times 8k would be bigger than 8 times 9, 72. So I'm using properties of inequalities. So there's a property that says you multiply both sides of inequality by a positive number, doesn't change the inequality. So if you have a greater than inequality multiplied by a positive, stays as is. And another property says if you add a number to an inequality, the two sides of the inequality stays the same. So if I add 9, this would be the same. And here's the last step we're going to work with. I'm going to take the square root. And the square root is if you look at it as a function, it's an increasing function. So if you take the square root of something, that is greater than something else, that order still holds, okay? So the square root of ak plus 9 here would be greater than the square root of 72 plus 9, which is 81, and the square root of 81 is 9. And therefore, ak plus 1 is greater than 9, and therefore, I have proven that the inductive step, and therefore by mathematical induction, this statement is true. An is greater than 9 for all positive integers. Okay, so on the next video, I'll go over the decreasing part. And yeah, please stay tuned. Thank you.